Hi everyone, and welcome to section 1.1 of Kinematics, and this is specifically 1.1 and part 1 of a 4-part series. And in this first part, we're going to be discussing velocity versus time graphs with constant motion. Okay, and what are velocity versus time graphs, and how and what's the utility purposes of a velocity versus time graph? Okay, so if you haven't done the reading, please do the Coletta reading, which is chapters 1, 2, and 3. If you're in college physics, do OpenStax chapters 2 and 3. Or if you're in 121, Physics 121, chapters 2, 3, and 4. Also, if you haven't gotten started, please get started with your homework. Okay, it's a good combination. It will help you out. Okay, so here we go. Velocity versus time graphs are basically just that. You're representing velocity over time, over a period of time. So what we had talked about before is that velocity could be positive or negative, right? It's not, speed is neither positive nor negative. It's just a number, right? It's a magnitude. But velocity has direction with it, right? So maybe what we could do is we could represent this motion on a number line, okay? So I've just input a number line on the notes section. So here we go. We have this first graph. Let's just take a look at this first graph and let's try to interpret what it is saying. So graph A, what is graph A saying? Well, this is what is going to appear essentially on your speedometer, but it also whether you're in drive or reverse. Right, so your car is going to be driving in the horizontal direction. Okay, we're not going to worry about your position specifically. Okay, so we're not really going to worry about this right here. Let's not worry about that. But what we're going to be worrying about is what is represented here. Okay, so on our graph, for graph A, you've got an object that at the 1 second mark, 2 second mark, 3 second mark, and 4 second mark. Okay, so let's interpret what is being said here. So at the 1 second mark, the red line is saying that you have a velocity of 0 meters per second. At the 2 second mark, you also have a velocity of 0 meters per second. At the 3 second mark, you have the red line is your velocity, so that is also 3 seconds. And then finally at the 4 second mark, you have a velocity of 0 meters per second. So what is that saying? If your velocity is 0 meters per second, 0 meters per second, 0 meters per second, 0 meters per second. And so what I like to do is that, am I moving to the right? Am I moving to the left? Or am I not moving? What would you categorize that if your velocity is 0 meters per second for all time increments? What are you doing? So what that says to me is that maybe you're at a position of, and I'm just going to put positive 10 meters, or yeah, let's just do 10 meters here. Okay, so you're at a position of positive 10 meters, and if you're at the 0 second mark, you're just here. So you have at the 0 seconds mark, you've got a position. So you've got a velocity of 0 meters per second. Well, that means you're just at the 10 meter mark. You're not moving. And then at the 1 second mark, you're also still here. At the 2 second mark, you're still there. And at the 4 second mark, you're still there. So what is that saying? Well, that says that you are not moving. So graph A is an object that is not moving. Its velocity is 0 meters for every second that you're seeing here. So this interpretation is the velocity over a period of time, and you have to figure that your velocity is in the horizontal direction and it's 0 meters per second. Okay? All right. Let's try graph B. Graph B is saying something different than graph A. Graph A is you could actually call this graph A. You could also call this a constant velocity of 0 meters per second. Well, graph B here, it looks like at the 1 second mark, and then this is a 2 second mark, and then the 3 second mark. Well, at the 1 second mark, it's got a velocity of -5 meters per second. The 2 second mark, it's got a velocity of -5 meters per second. And at the 3 second mark, it's also got a velocity of -5 meters per second. And then finally, at the 4 second mark, it's got a velocity of -5 meters per second. So what is that saying? Okay, well, that's saying, again, that this object, let's say it started out here, and this is going to be +5 meters, +10 meters, +15 meters, and +20 meters. I'm going to just put my number line in the constant increments, 15 meters, -20 meters. Okay, well, graph B, let's say the object, for us to represent its velocity, we could have it being at negative positions. This is just a velocity versus time graph. It's not telling us where we're initially starting. So what I want to do is I'm gonna want to use positive positions, and the reason why is our position versus time graphs are only considering positive positions. So if this object is traveling to the left the entire time, it's got a negative velocity the entire time, and so I'm going to have it start at its furthest position. So at the 0 second mark, graph B is going to be starting right here, and then it's going to travel another 5 meters to the left, and it's going to travel another 5 meters to the left, and then finally another 5 meters to the left. And then it's going to be right where we're at, right at the origin. So at the 4 second mark, this is the 3 sec. Oh boy, kind of made a mistake. Couple mistakes there. Sorry about that. This is 0 seconds, 1 second, 2 seconds, 3 seconds, and then finally at the 4 seconds mark, it's right on top of us, right? So I don't know if I filled in the graph for graph A. It was at the +10 meters, and we just showed it sitting there the entire time for the 4 seconds. But this one right here, this guy seems to be starting out at a position of +20 meters, and it's at +20 meters at that point. And then it's going to be at the 4 second mark at this point, and it'll be at the 0 meter mark at 4 seconds. So it looks like this object is traveling this way. So graph B, this is graph A. Graph B starts out at the 20 meter mark. So at the 0 seconds, it's at 20 meters, 0 seconds, 20 meters. And then it's traveling at a constant velocity to the left of 5 meters per second. So this velocity, the instantaneous velocities at each one of these points, is going to be -5 meters for every second that it moves, right? -5 meters, -5 meters, -5 meters, -5 meters, -5 meters. And that translates to traveling a displacement vector of -5 meters for every second, right? So that shows that this guy is traveling to the left. Okay? And it's going to have a negative velocity. Okay? Even though its positions are positive. So right here at the 2-second mark, it was at positive 10 meters. Okay? At the 2-second mark. So that's pretty cool. Let's try graph C. I'm going to have to erase the graph B's information here. Get a little crazy erasing there. This should be 10 meters, this will be 15 meters, and this will be 20 meters. So this is positive 10 meters. So looks like graph C at the 1-second mark, it's got a positive 5 meters per second. At the 2-second mark is positive 5 meters per second. 3-second mark, positive 5 meters per second. 4-second mark is 5 meters over 1 second. So let's have this start off at the origin. We don't know its starting position from the velocity versus time graph. All we know is its velocity at each point in time. So you could have it starting off right here. In fact, I'm going to have it start off right here at the 5 meter mark. Okay, so it's going to start off here at the 0-second mark at 5 meters. I'm going to use green to represent this guy. So this is graph C. And it's starting out right here. So this is graph C. All right, and it's starting off at the 5 meter mark. Okay, it doesn't matter at time 0 seconds right here. This is 0 seconds. At the 0-second mark, all you know about that is that it is at 5 meters per second. It's got a displacement of 5 meters for every second. You don't know its position. Okay, you do know its displacement. You don't know its position. Okay, so you could have it start off with an initial position of wherever you want. I'm choosing 5 meters, positive 5 meters. So here we go. At the 1-second mark, it's at 10 meters per second, and that means it's traveled to the right. Here, it's 2 seconds, 3 seconds is at the 20 meter, and then I'm going to have to add the 4 seconds over here, and it's right here. And I'm actually going to have to add to the number line. And now it's going to be at the positive 25 meter mark. Okay, and I'm just doing that for a point, and for the point of that it's going to end up here at the 25 meter mark, and it started out at the 5 meter mark, positive 5 meter mark. Okay, this is 4 seconds. So this is an object that starts off at the 5 meter mark at 0 seconds, and then ends up at the 25 meter mark at that point in time. And that means its velocity is going to be positive, and its displacement is going to be 5 meters for every second. So, well, the wonderful thing about this is that you could, about a velocity versus time graph, is that you could actually figure out it'll tell you what its velocity is at each point in time, but it doesn't tell you its position. So you kind of have to put in your own starting position and make it up. And that each object, in this case, is going to be a constant velocity object. A velocity versus time graph can represent constant velocity, but also accelerated motion, like speeding up and slowing down too. I didn't mean to confuse you there. But in this particular case, all of our objects are traveling at a constant velocity, and this is constant velocity of -5 meters per second. And this is a constant velocity of +5 meters per second. Okay, so you can immediately see its speed. But here's the cool part too, is that you actually can see its displacement, right? If the object, let's do this one. For the object, this guy, for this particular point in time, it was traveling at -5 meters for every second. So in this particular first second, it traveled -5 meters. In the next second, it traveled a -5 meters. In the third second, it traveled a -5 meters. In the fourth second, it traveled a -5 meters. So overall, that looks like graph B, its displacement, actually I'll represent it this way, its x direction displacement of graph B, its total displacement was -5 plus -5 plus -5 plus -5. That would be a total displacement of -20. Graph A, it was not moving at all. And that's graph A. It was not moving at all. So its displacement was 0. Graph C, its displacement was +5 meters for that first second, +5 meters for the second second, +5 meters for the third second, +5 meters for the fourth second. So its displacement is +20 meters for that entire 4 seconds. Okay, so the object A, graph A, had no displacement. Graph B had a -20 meters displacement for that 4 seconds, and graph C had a +20 meters displacement for that first 4 seconds. So a velocity versus time graph is very powerful, and that allows you to represent displacement and velocity, and you could easily get those equations. The only problem is it doesn't tell you the initial position of the object, and you have to figure that. You have to just establish it, right? Or ask the question, where did the object start out moving? Okay? Well, a secondary usage of that, of a velocity versus time graph, other than just seeing what the velocity is over each increment of time, is that the area relative to the 0 meter mark, relative the area under the curve, or relative to the 0 meters per second mark, will actually tell you the displacement of the object. Okay? And for my calculus students, you just actually integrate a velocity versus time equation, and that actually will tell you the area under the curve, or the displacement of the object. Okay? So the best way to do this is with an example. Okay. Well, here we go. So here we have an object that is going to be, this is a velocity versus time graph. So these are all positive velocities. So at the 1 second mark right here, it was traveling at 4 meters, at a +4 meters for every second. At the 2 second mark, it was traveling at a +8 meters for every second. And I'm just double checking this. +12 meters per second for every second at the 3 second mark. So it looks like we're only looking at the data from 0 to 3 seconds. Okay, so we're not worried about the 16 second mark or the 4 second mark. Okay. Well, in a velocity versus time graph, we could actually create an equation. Okay. Again, this is a linear equation, right? And we're going to use y. Again, we're going to just use the basic y is equal to mx plus b, right? Well, the y-axis is velocity, so you're going to be trying to predict final velocity. So the y-axis is velocity. You're going to try to predict final velocity given an initial velocity. The y-intercept will be the initial velocity, right? And here it looks like the y-intercept will be 0. The mx, the slope is going to be rise over run. So it'll be final velocity minus initial velocity over final time minus initial time. Well, velocity over time is actually your acceleration. So in this case, slope is the acceleration of the object. And again, the x-axis is time. So a linear curve fit in a velocity versus time is going to be v final equals the slope, which is acceleration. The horizontal axis is time, given the initial velocity of the object, which is the y-intercept. Okay. So let's try to figure it out. What is the slope of this object? Well, in this case, so it's a line. We could say it ended at a speed of 12 meters per second. It started out at a speed of 0 meters for every second. It started out at 0 meters for every second at time 0, and it ended at 12 meters per second at time 3 seconds. So in this case, the object is going to have a change in velocity of 0 meters of positive 12 meters for every second over 3 seconds. So that is going to work out to be positive 4 meters for every second squared. Or what you could also say is velocity is changing by 4 meters per second for every second. I actually kind of like that better. It's better to say that the velocity is changing a positive 4 meters per second for every second. Okay, and we'll talk a little bit about acceleration here in the next section. So if you wanted to, you could integrate this equation. So we're going to now translate this here to a velocity. We have a positive 4 meters per second, delta t. So I'm just going to put a t here, plus 0. It started out with 0 meters per second, and this is a 4 meters per second squared. Well, you could choose to integrate this, okay? But there's a trick. There's 2 things that you could do, and I want you to be smart about how you select to do this, right? Well, the point is, and we saw from the last slide, that the area relative to the 0 meters per second mark is going to be the displacement. Well, if you look at this blue area relative to the 0 meters per second mark, so the area under the curve here, is a triangle, right? So rather than integrate, trying to, we're going to get displacement, and displacement is this equation v of t dt, right? So rather than doing that and doing this whole linear equation, which is going to be 4 meters per second t plus 0 meters per second dt, rather than doing this from 0 seconds to the 3 second mark, rather than integrating that, can't you just do the area of a triangle? If this is the same thing as the area under the curve, can't you just do the area of a triangle? Right? So isn't the area of a triangle just 1/2 the base times the height? And in this case, the area of a triangle is going to be equal to 1/2 the base, which is 0, 1, 2, 3 seconds, times the height, which is going to be 0 to 12 meters, right? 0 to 12. 12 meters per second. So hopefully when we do both of these things on the next page, it's going to work out. This is going to be, what's 12 divided by 2 is 6 meters per second times 3. 6 meters per second times 3 is going to be 18 meters. Hopefully this is going to work out to a displacement of 18 meters. So if we actually did this integral, this would work out to be, and sorry about the nature of this, is going to be 4, so this will be t squared, so this is going to work out to be delta x is going to work out to be, what is that, 4 meters per second t squared divided by 2 from 0 seconds to 3 seconds. So that t squared, now we're going to put in 3 seconds and square it, so that'll be what? That'll be 3, that'll be 10, that'll be, so this will work out to be, what is that? 3 squared will be 9. 9 times 4 will be 36. 36 divided by 2 will be 18 meters. So this will also work out. So you could do both ways. This is a very mathy way to do it, but this is a more conceptual way where if you say an integral, the definition of integral to me is the area under a curve, well, area relative to a zero mark. Well, then that is the same thing as doing this. Well, let's check our work and see what happens. And it looks like they did the same way we did for what you would do in college physics, which is just take the area under the curve. Okay, so they called, again, the area under the curve is 1/2 the base times the height. It was 3 seconds is the base, 0 seconds. So this will be 3 seconds minus 0 seconds. And the height will be 12 meters per second minus 0 meters per second, right? So this is actually 1/2 delta t times delta v. That's really what they're saying, is that. And they got 18 meters, which is what we got when we did both methods, the area as well as the integral. Okay? Well, what I want you to do in this next example is I want you to do both, okay? What I want you to do is I want you to plot this equation right here on this velocity versus time graph. And then I want you to get the displacement using the area method, but then I also want you to integrate it if you're in Physics 121, and then just double check your work and integrate this with respect to time to actually get what the answer is using the integral of that. Okay? So take a moment, pause the video, translate this equation to a velocity versus time graph. And then what I want you to do is just find the integral of that. It'll probably be a triangle. Okay? And then after that, for physics, if you're in Physics 121, I want you to then, on top of that, integrate this equation right here to double check your work as far as the area of that triangle. Okay? So this is an object, starts out at -4 meters per second, and then it's going to have its velocity changed at a positive 6 meters per second for every second. Okay, this is a positive 6 meters per second for every second. So its velocity is changing by a positive 6 meters per second for every second. All right, go ahead and try this now. Hit pause. Okay, we are back. Well, at the 0 second mark, so this is the format. We're trying to predict final velocity given an acceleration times delta t plus the initial velocity. In other words, we're doing y is equal to mx plus b, right? Well, this is just a linear fit. At time 0 seconds, it's going to have a -4 meters per second. Maybe what I should do is actually think about this for a second a little bit more. And what I'm going to do is I'm going to actually erase this here. I don't want it to start off. We're going to have to take a time frame from 1 second to 4 seconds, right? So our time is actually going to start off at, actually we do want the time to start off at 4 seconds, so I'm going to change the nature of the question here. Well, I'll change it afterwards, but I'm going to change this from 0 seconds to 4 seconds, right? Actually, let's just leave it at 1 second. It'll be fun. It'll complicate it. So what I'm going to do, here's what I'm going back and forth about, is the fact that we're going to be starting off here. So our time is going to start off at 0 seconds, right? And this is where the negative 4 second mark occurs. But we're going to be taking data from 1 second to 2 seconds to 3 seconds and then to 4 seconds, right? And if you notice, it changes quite a bit, right? So at this point in time right here, so at the 0 second mark, and maybe I want to spread this out too so I can draw a nice picture. So 1, 2, 3, and then 4. Yeah, that's what I'll do. 2 seconds mark, 1 second mark. So at the 0 seconds mark, it starts off with a initial velocity of negative 4 meters per second. Now it's going to be increasing. It's going to be adding a positive 6 meters per second for every second. That means in the first second, its slope is going to go from negative 4 to positive 2 meters per second. So after the first second, and I'm going to use red to plot this, after the first second, it's going to start off at negative 4, and then in the first second, you're going to add 6 to this. So negative 4 plus 6 is going to be positive 2, right? So that's what I'm saying, is I needed to change the nature of my graph, right? So this graph, as I've drawn it, I'm going to have to change, well, I'll just keep it right here, and I'll just increase this scale right here. So now it's going to be right here. For the first second, so from the 0 second mark, it was right here at negative 4 meters per second. And then after the first second, you're going to add 6 to this, so 6 meters per second to here, which is going to make it positive 2 meters per second. Now you're going to add another 6 for the next second, all right? Well, the next second, it's going to now be at positive 8 meters per second, right? Because positive 2 meters per second plus 6 is going to be a positive 8 meters per second. And then you're going to add another 6 to that, which is going to be 8 plus 6 is going to be 14, is going to be up here. And I'm trying to space these so it's making a line. And then finally 14, which is going to then be 18. So the increments that we're going to be going at here, that we're going to be using, is going to be positive 14, and then positive 14, it'll be then positive 20 meters per second, right? So this is going to occur at positive 20. This will be 20 meters per second at the 4 second mark. This will be positive 20. This will be positive 14 meters per second at the 3 second mark. And then you got positive 8 meters per second, positive 2 meters per second. Then you have negative 4 meters per second. Okay. Well, let's go ahead and try this now. So we've we've graphed this, and I feel like I've graphed it correctly, and I could be wrong, I could be off, but it looks like this slope from 2 to 8 is going to be positive 6. So this line is going to be from the 2 second mark minus the 1 second mark. So it's going to be rise over run. So 8 meters per second minus 2 meters per second over 2 seconds minus 1 second. That's going to be 6 meters for this second. So this is going to be positive 6 meters per second. So it looks like I've got this correct. So each one of these slopes is positive 6 meters per second for every second. Okay. Well, if we now look at this, the area under the curve, area relative to the 0 mark, is going to be this. It's going to be from, we're trying to get the displacement from 4 seconds to 1 second. Well, that has to go to the 0 mark. Okay. So the displacement, it starts off at the 2 meter per second mark at time 1 second, and then it gets all the way to the 4 meter per second mark. So this sucker is rising. It starts off here at the positive 2 meter per second mark and ends up at the positive 20 meter per second mark. So it's going to rise a total of 18 meters per second. So yeah, it's going to rise, it's actually rising 2 meters per second for from 2 meters per second to 20 meters per second. But we can't forget that this is the area under the curve relative to this 0 meters per second mark. So we still have this 2 meters per second for every second that we have to take into account. So in a way, this is a triangle plus a rectangle in here. Okay, so let me say that again. It's relative to this 0 meters per second mark. So even though the area goes from 2 meters per second of the triangle to 20 meters per second, the area under this line right here goes to the 0 meters per second mark. I know that sounds a little weird. Even though it's starting at the 1 second mark at 2 meters per second, you still have to account for this area underneath too as well. Okay, so in a way, to get this area, the total area under the curve, you have to go the area of this black area right here, which is 2 meters per second, right, times 1 second, 2 meters per second times 1 second, 2 meters per second times 1 second, okay? So that's the area of a rectangle plus the area of the triangle, and that triangle goes from 2 meters per second, 20 meters per second, and also 1 second to 4 seconds, right? So the total area there is going to be the area of this rectangle, which is 2 meters, rises 2 meters per second over 1, 2, 3 seconds, right? So it's going to be 2 meters per second times 4 seconds minus 1 second, plus the area of the triangle, which is 1/2 the base, which is 4 seconds minus 1 second, and the height is going to be 20 meters per second minus 2 meters per second. Okay, so that total area is going to be, what is that? 2 times 3, that's going to be 6 meters, plus, what is that? That's 3 seconds, and this is going to be 18 meters per second. 18 divided by 2 is 9, times 3 is, so that's 27 meters. So this is going to be that total area, is going to be a total area of 33 meters. Well, let's verify this by doing calculus. Okay, so if you're in college physics right now, go on, advance it a little bit and go on to the next slide. But if you want, you could stick around and watch what the Physics 121 students are doing. Okay? So we're going to actually take this, and I'm going to copy this whole thing. And we're going to do some calculus, and we're going to use Microsoft Whiteboard to do it. Okay? So I'm going to click on here, start a new whiteboard. And then we're going to put our work right here. And then I'm going to expand upon this. Okay? So we're going to do calculus in here. Okay? So the velocity is equal to displacement over time, right? Which is like saying dx dt, right? Multiply both sides by dt. Dx is going to be equal to v dt, right? And this v is actually going to be our v of t equation right here. And dt is going to be our time frame from 4 seconds to 1 second. And dx is just going to be the displacement, right? So what we're going to do is really we're translating this to xi to xf because I don't know the displacement. So I'm just going to define it relative to dx. Our v of t equation is going to go right here, which is our positive 6 meters per second over every second times t minus 4 meters per second. And that's dt. And we're going to do this from the initial time to the final time. Okay, so that's our general equation, right? Well, keep running this further. This is just going to be delta x, right? This is going to end up being x final minus x initial, all right? And this v of t is going to be our v of t equation, and that's going to go from 1 second to 4 seconds, right? And that v of t equation is positive 6 meters per second squared, t minus 4 meters per second dt. So this is our v of t equation right here. And I am just going to call this delta x. Okay. So I'm going to carry this down to here. This is 6. So delta x now is going to be equal to 6 meters per second squared t minus 4 meters per second dt from 1 second to 4 seconds. So now I'm going to integrate this. I'm going to integrate this first part. That's going to end up being 6 meters per second squared t squared divided by 2. And then the negative 4 meters per second I'm going to integrate. And that's going to be minus 4 meters per second times t. And this is all going from our 1 seconds to 3 seconds. 1 second to 4 seconds, I should say. All right. Well, let's go ahead and plug in our 4 seconds into this. So this is going to be 6 meters per second squared. I need a little bit more room. So this is our 6 meters per second. Let me rewrite that. 6 meters per second squared. And our t, we're going to put in our 4 seconds, and we're going to square that and divide it by 2. Minus 4 meters per second times 4 seconds. Okay, and this is our 4 seconds mark. And now we're going to put it in our 1 second mark, our lower part of our limits, which is going to be 6 meters per second squared times 1 second divided by 2 minus 4 meters per second times 1 second. Okay. All right, well, let's think about this for a second. This whole thing right here is, this is going to be, so this is our delta x. 6 meters per second times 4 seconds, so 4 seconds squared, 16 divided by 2 is going to be 8, 6. So what is that going to be? That's going to be 48. So this is going to be 48 meters minus 16 meters minus, and this is going to be 6 times 1 divided by 2, which is going to be 3 meters minus negative 4 times 1, so that's going to be minus 4 meters. So overall, this is going to be 32 minus this, so 32 minus a negative 4, and that is going to work out to be 33 meters. So using the same method, using calculus, we're confirming our area as 33 meters. Okay? So that's very cool that we could actually get the area under the curve. Okay? Using calculus to do this and get the displacement of the object. Now we know the displacement here. This is all this is saying here, and we just confirmed it with calculus, is that the displacement here is 33 meters. But if you, and that's a positive 33 meters. So it's moving. We know this object has moved to the right 33, a total distance of 33 meters. But we don't know where it started out at. So that's kind of the problem with velocity versus time graphs if you're using it to get displacement. You just know how far its displacement was to the left or to the right, but you don't know exactly where it started out at. Okay? You just need that little bit of information. Well, now I want you to go ahead and apply that to this problem. What I want you to go ahead and do is, we're going to do something a little bit different, is I want you to actually, we're going to actually do a couple things here. I want you to create a series of linear equations from 0 to 1 second, to 1 to 2 seconds, and 2 to 4 seconds, right? So I want to help you practice your linear equations and getting those velocity versus time prediction equations. And then I want you to figure out what his total displacement was from 0 to 4 seconds, okay, using whatever method that you want. I would, in this case, I'm going to encourage you to use the just the area under the curve and use triangles to do this. And then finally, I want you to actually figure out its average acceleration from 0 to 2 seconds. Okay, and that's a little bit different, right? So again, I'm going to write the acceleration equation here. Okay, I haven't done that yet, but I'm going to introduce the concept of acceleration here. So we're practicing something that we're about to actually start working with, which is the concept of acceleration. But I want to introduce it to you just in a mathematical sense, okay? And you're going to use the same thing to get acceleration, average acceleration, like you did with average velocity and position versus time graph. You're going to now just apply it here. So acceleration is your change in velocity over the change in time. Okay, and we've kind of talked a little bit about that. We're going to get more into it in the next section. But the average acceleration is not this velocity plus this velocity divided by 2. That's the statistical average velocity, but that is not the physics concept of average velocity. Okay, so I want you to try to use the concepts you learned from the velocity versus average velocity using position versus time graph, and try to see if you could actually try it here. Okay, so I'm trying to get you to leap a little bit. Okay, let's go ahead and pause the video and try to get all of these. Okay, so please pause the video now. All right, here we go. So you're asked to start to get prediction equations, linear prediction equations for each one of these time increments. And again, you're going to be doing y is equal to mx plus b. But in this case, you're going to be predicting final velocity using using slope delta t plus initial velocity. Okay. Well, here we go. What was your initial velocity here? Well, it is 0 meters per second. And you're noticing I'm starting out with the y-intercept. I always find that's a lot easier. Delta t. I want to give myself a little bit of room. Delta t. Okay, that's going to be, and then I'm going to do the slope part. Well, what is the slope here? Well, it looks like it's 0. So that slope is, that velocity is changing 0 meters per second every second. So this is the velocity from 0 to 1 seconds. Okay, so that's the prediction equation for that, which is, what that's saying is no matter what time increment we choose here, it's going to predict our velocity to be 0. Because it has no acceleration and it has no initial speed. All right. Let's try the next one. We're going to be doing this from 1 to 2 seconds, right? So it starts off at 0 meters per second is its initial velocity. And it's going to end at 20 meters per second, right? So the slope here, it's going to be 20 meters per second minus 0 meters per second all over 2 seconds minus 1 second, right? Which is actually what this is, right? Which is going to be 20 divided by 2, which is going to be, and that's a positive 20 divided by 2, which is going to end up being a positive 10 meters per second change for every second, delta t, and this is the velocity from v12. Let's do the v23 equation. Okay. Well, this slope, it's going to be negative, and it's now changing from 20. So it's ending at 0 meters per second, and it started out at 20 meters per second. And I should say it started out at a positive 20 meters per second over 4 seconds minus 2 seconds. And let me just change this. I realize that should be a 4 to 4. So this is going to end up working out to be negative 20 divided by 2. So this is going to work out to be a negative, hold on a second, I just realized this should be 1 second. So this should work out to be positive 20 meters per second, and this is going to work out to be negative 10 meters per second, delta t, and it started out at 20 meters. Okay, fix my error, and also fix this. Okay, cool. Those seem accurate to me. Okay. So now let's try something else. Let's figure out the displacement. Okay. And there's a quick way to get a couple things here. If you look at this block right here, the area of this block, or each one of these blocks, is 10 meters per second over every second, right? So each block represents 10 meters per second, right? So this is an area of 10. Well, this is an area of 10, and this is actually half that, so that's 5 meters per second squared. And this is 5 meters per second as well. So this area right here, we could say is so we're going to get the total area, and that's going to be the area of the triangle here, which is this guy. I'm going to use this area so we're going to get the area of this triangle here, so area of that triangle, plus this area. Well, we've kind of already got that area by making an estimate. If each block is 10 meters per second, and this is half that other block and half that, that's going to be 10 plus 5 plus 5. So the displacement here is going to be 10 meters. I don't know why I put the seconds in this. This displacement is going to be 10 meters plus 5 meters plus 5 meters. So this is going to be a total of 20 meters. The block is 10 meters, and half a block and half a block, 5 meters and 5 meters. Well now, and that's all relative to the 0, right? Well now let's do this triangle. Well, the area of that one triangle is going to be equal to the base. So it's 1/2 in the base, which is 2 seconds minus 1 second. And that rise is going to be 20 meters per second minus 0 seconds. Minus 0 seconds. And that's plus 20. So overall, this is going to work out to be 20 times 1 divided by 2, which is going to be 10. So overall, this displacement is going to be 20 plus 10. So that's actually going to be 30 meters in the positive direction. So we know this object moved 30 meters in the positive direction. Okay. Pretty cool. The last thing that we're going to do is find the average acceleration. And again, the average acceleration, okay, is going to be the velocity. I'm going to put little vector heads on those things, divided by time, right? And the average acceleration is a vector. Well, what is the velocity? And we're doing from 0 to 2 seconds. Well, at the 2 second mark, so the final velocity is going to be 20 meters per second at the 2 second mark. And it started out at 0 meters per second at the 0 second mark. So the average velocity of 0 and this 20 meters per second is going to work out to be 20 divided by 2 is going to be positive 10 meters per second, or positive 10 meters per second squared. Okay? Which is weird, right? It's not the statistical average. I just want to point out that this is 0 meters per second squared plus 20 meters per second squared, right? And so in this case, the statistical average, if you divide that by 2, happens to work out to be 10 meters per second, but that is not, that's just a coincidence, right? Because if we did the average velocity from time 0 to time 4, right? So if we did the average velocity from time 0 to time 4, well, it starts out at 0 meters per second over here, 0 meters per second, and it ends at 0 meters per second from time 0 to time 4 seconds. Well, that is going to be 0 meters per second squared. But the average velocity in this case would not be that. It would be 0 meters per second. I'm going to alter this. So here's where statistical average is different from average velocity as determined by physics, is the true average velocity. You're not doing this. The statistical average velocity, you're doing 0 meters per second squared plus 20 meters per second squared minus 10 meters per second squared divided by 3, right? Because you have 3 of those. That's 20 minus 10, so that's 10. That's 10 meters per second squared divided by 3, so what is that, like about 3? Well, that 3 meters per second squared is the statistical average. It's actually 3.33 meters per second squared. But that is not what the physics average acceleration would be. So that's kind of the difference between, again, average velocity and statistical average velocity, right? And that's kind of what we did when we were finding out what average acceleration and statistical average acceleration. It's kind of what we did when we were finding average velocity too, right? So hopefully you learned a little bit here. Well, now what I want you to do is I want you to go ahead and I want you to relate graphs A and B to graphs 1 and 2 to graphs A and B, and then I want you to create some prediction graphs for graphs 1 and 2 here by filling in the blanks. Okay? So go ahead and pause the video and see if you could go ahead and do this. Okay? All right, here we go. So what we're going to do is we're going to actually really quickly, you could actually do this very quickly, is relate graphs. Which one of these graphs graph A goes with graph 1 or graph 2? What do you think? Well, graph A is showing the object has a velocity of positive 5 meters per second, a constant velocity of positive 5 meters per second over 1 second. Graph B is showing that this object, graph B, has an average velocity of, and I'm going to just put some numbers, and this is supposed to be the halfway point, by the way. The intended is this is going to be positive 2.5 meters per second over a period of 1 second, right? Well, that is supposed to go with this, right? So it looks like graph A goes with 2, right? Because it's steeper. This constant velocity is a higher velocity, and the higher velocity here in a velocity versus time graph goes with a steeper position versus time graph. B is a more level versus time graph, and that's 2 meters per second over the entire time. Okay? And the cool part here, we could actually figure out what its displacement is here really quickly, right? 5 meters per second over 1 second, so that's the area of a rectangle. So its displacement here is going to be a total distance of positive 5 meters. This guy's area is going to be a total displacement of 2.5 meters, right? So, well, even though we know that displacement, we don't know where it started out at. That's where the position versus time graphs. They both start out at a position of 0 meters. Okay, so we could actually put that in right here. Both objects are starting out at 0 meters. But object 1 goes with graph 1. That looks like it has a velocity or a slope of 2.5 meters over 1 second, and that's a positive slope. So this is 2.5 meters per second, and the other one is a positive slope of positive 5 meters per second. So now what I'm trying to do is get you to relate velocity versus time graphs to position versus time graphs, as well as their displacements, and figure out what velocity is and create prediction equations for position versus time graphs using velocity versus time graphs. So that was the point of this. So now we're going to go in, and we've kind of been talking about what acceleration is a little bit in mathematical terms, but in the next section we're going to talk about the conceptual understanding of acceleration and then relate it back to this stuff in velocity versus time graphs. I hope you had fun, and I will see you next time. Bye.